Hi, Dr. Lyons here, of course. This video introduces concepts related to statics and static equilibrium for mechanical engineering analysis of a simply supported beam like this 2x4 here. Enjoy. So I've got the beam rested here on some 2x4 blocks, and those are sitting on a couple of bathroom scales. And this is basically an experimental setup that students might use in a lab that I might have them do in my mechanical engineering course. The beam is called simply supported because the supports are very simple. They're not bolted to the supports, they're just resting on them. And what we're going to do here is illustrate how the value of the scales change, how the force measured by the scales changes as I stand on different positions on the beam. I'm going to say for the purposes of today's video that I weigh about 180 pounds as I'm dressed right now with everything in my pockets. And if I was to just stand on one scale, it would indicate 180 pounds, of course. The question is, what will each scale read if I stand in the middle? Well, if I stand directly in the middle, then my weight should be equally divided between those two scales, and they should each read about 90 pounds. If I stand all the way over here on the right scale and put all my force on the support, that scale should read 180, which is my weight, and the other one should read 0. As I'm moving across the scale, then the one on the left starts to read lower and lower forces, and the one on the right starts to read larger and larger forces. But always the sum of the two forces, from which we call reaction forces, measured by the scales, always the sum of those reaction forces will add up to the weight that I'm applying to the scale, regardless of where I stand. So some of this stuff is pretty simple to figure out. If I'm standing in the middle, each one should give a reading that's about half my weight. If I'm standing at the quarter point, then the distance from me to that scale is the length of the beam divided by 4. And the distance from me to that end of the scale is the length of the beam times 3/4, or 3/4 of the length of the beam. So if I'm standing right here at the quarter point, that scale on the left should read 3 times the value of the reaction measured by the one on the right. Last, we can do a static analysis which will result in some equations that can tell us the force at one reaction for any position of my body on the beam. If I stand in the middle, quarter point, 5 inches from one end, I can derive some equations from static analysis that will tell me exactly what that scale should be reporting. The purpose of a laboratory experiment would be to compare how the actual measurements of those reaction forces compare to the theoretical values. So let's talk about how to model the simply supported beam. The first concept that I want to introduce is called a free body diagram. The body that I'm interested in doing the analysis on is the beam. So when I draw a free body diagram, I draw a picture of the beam without any of the other details associated with the supports on there. I'm not interested in the forces in the blocks that the beam was sitting on or how the scale is sitting on the floor. I'm only interested in the beam itself because that's what is being used to apply my weight to the scales. So a free body diagram for the beam could be as simple as a long rectangle. So this is a sketch of the beam. And I am applying a load to the beam somewhere along the length of it. I'll say that vector represents the force that I'm applying to the beam. And I'm a person, so I'm going to call that force P. Now, if there weren't any supports and I was standing on a beam floating in space like this, the beam would just fall under the application of that force in addition to the gravity. So I've got reactions that are acting up at the two ends where the where it's sitting on the scales. And so I represent those reactions also with vectors, and I'll call this one over here at the left R1, and I'll call the one over here at the right R2. So this is the free body diagram of the beam. I want to be able to calculate from a theoretical perspective the value of R1 and R2. So I need an equation. I can see from inspection one of the equations, which is that the force acting down is going to have to equal to the sum of the two forces acting up to prevent this thing from moving. So the first equation of equilibrium is that the force P is equal to the sum of the two reaction forces. So this is can be seen from sort of some common sense that the reaction forces have to add up to the force that's applied. The way we generally would approach this for a more complicated problem is by saying that the sum of the forces equals 0. So using the Greek big sigma for sum, I will say that the sum of the forces equals 0. So for this particular problem, all my forces are acting in the same direction, which makes things a lot easier, but I would generally want to have a coordinate system associated with my free body diagram. And I'll put that here at the end of the beam. And so I have a direction x, which is going along the length of the beam, and a direction y, which is going up and down. And if I wanted to be precise about the way I've written my sum of my forces equation here, this particular case represents the result when you sum the forces in the y direction equal to 0. So the forces in the y direction equal 0. The way I've drawn my scale, the way I've drawn my coordinate system, up is positive. So if I'm writing the static equilibrium equation, I've got the sum of forces y equals 0. R1 is acting up, so R1 is positive. R2 is acting up, so I'm going to add that. And P is acting down, so P is going to be negative because I'm acting down. And that is the first equation of static equilibrium. From a theoretical standpoint, I may know what my load P is, but I don't know what R1 or R2 are. Those are my unknowns. I can't solve for them with just one equation. I've got two unknowns in one equation. So I need to know something else about how R1 and R2 are related. So they are related to each other through the position of the force that is being applied. Where is that P actually coming down on this beam? The distance from the reaction to the applied force, I'm going to call A. So in this particular illustration, my load P is applied to distance A from the left end. The other dimension that's important here is the total length of the beam, which we'll call length L. So L is the total length of the beam, and A is the distance from the end of the beam to where the load is being applied. That's all the geometry I really need to move forward with solving this problem. I'm going to go ahead and erase these equations. Let's talk about how do we get another equation to relate the two reaction forces and P. I need two equations to solve for my two unknowns, R1 and R2. Well, what I'll do is I'll use a concept called a moment. If the beam was free to move around in space, these reaction forces would be able to keep it from moving up and down. But the other type of motion that the beam could experience is rotation. So the beam was obviously not rotating when it was sitting on the scales and when I was standing on it. So we've got an equilibrium equation that's related with preventing rotation. And the way we derive that is from the concept of the moments about a point. Actually, it's the moments about an axis. So let me illustrate the concept of a moment using a wrench. This is a very small wrench, but if I put the wrench on a bolt or something and I push down right here, that's going to make that something twist. Now, if I hold my finger tight, I can prevent it from twisting as I apply a load down here. When I apply a load very close to that something, it doesn't really hurt my finger too much. I can resist that. But when I increase the lever arm and start pulling the load down right here, in order to prevent that from twisting, I've got to really torque down on my finger, and it actually starts to hurt a little bit. So a moment is a torque or a twist that's being applied to something. And the way it can be calculated is by knowing the force that's applied and the position of that force relative to the resistance to twisting. The other source of a static equilibrium equation is making sure that all the moments on the beam add up to zero. The concept of the moment can be represented as the force times a distance. So we have to know a measurement point, and I'm going to assume that. So we have to know a measurement point. So I'm going to use the end of the beam as my measurement point, and for this thing to be in static equilibrium, the amount of twisting that P would cause has to be balanced exactly by the amount of twisting that R2 would cause. Otherwise, it would move up or down. This reaction doesn't cause any moment at this point because the point is going, because the force is going right through the point. The distance R1 is from the origin is zero. So that if I'm summing the moments, adding the moments about this point right here, there's no contribution from R1 because it is at the point. P is going to act over a distance A, and it's going to cause twisting down, and R2 is going to cause twisting up. So for the static equilibrium, about O, at point O, then the moment caused by reaction P, which is P times A, has to be equal to the moment caused by R2 acting up, which is R2L. So with a simple problem like this, we can use logic to see the relationship between R2 and P. I've got an equation that has one of my unknowns, which is R2. So that's one equation with one unknown. And I've got another equation that has that variable and another one, which is R1. So I have a total of two equations with the two unknowns, R1 and R2. And I can solve those to find R2 as a function of P, A, and L only. For the case of R2, I can get that directly from this equation by dividing both sides by L. And R2 is going to be P times the quantity A over L. So regardless of what the P is, the relationship between the reaction and the force is going to be determined by this ratio of position to length. This is one way to use logic to talk about what the moments are. Usually when we're doing a more complex problem, we use the concept of the sum of the moments being equal to zero. And so one would write that as the sum of the moments about a point 0 equals 0. Now, the moments could cause twisting up or down, so it's necessary for me to define a direction of positive twisting. And I like to draw a little curly Q right there with an arrow on it, indicating that a counterclockwise twist is going to cause a positive moment. So if I'm using the sum of the moment concept to relate P and R2, I need to look at all of my reaction forces. Again, R1 is not part of this equation because it acts at the origin, and the next one to consider is P. Now P would cause a twisting to the down relative to the origin, or that would be opposite the direction that I've drawn my reference twist. So I'll write minus P times A for the moment of P about the origin. And R2 would cause a twisting that's in the same direction as I've drawn for my my twisting coordinate. And so that will be R2 times the distance from there to the origin, which is L. So if I solve this equation for R2, I get R2 is equal to P times A over L. Again, this is an equation that I wrote down earlier just from using some logic to deduce what was going on. But this is how you might write out an equation for having multiple loads. Let's say somebody else stands over here and his name is Bob, and we could have another distance measured where Bob is standing. That would give us another term in the sum of the moment equations. And for more complicated problems with multiple people standing on the beam, you're probably going to want to start with this sum of the moments equals zero concept rather than just starting to logic and use your logic and deduce what's going on. So I've got an equation for R2. I'm going to erase Bob. So now I've got two equations. The one I just erased, which is R2 is equal to P times A over L. R2 is P times A over L. And then I've got the equation that was R1 plus R2 equals P. R1 plus R2 is equal to P. I can rewrite that as R1 is equal to P minus R2. And solve for R1 by substituting the first equation into the third. And so R1 is going to be P minus R2, which is P times A over L. And I've got an equation for R1. I like to simplify things, so I'm going to factor out a P, and I'm going to factor out a P, and I'm going to get P times the quantity of 1 minus A over L. So now I've got an equation for the first reaction force, R1, acting at the origin there as a function of the applied load and the dimensions. And I've got an equation for the other reaction, R2, which is also a function of P and the dimensions only. The choice of putting the origin here on the left was purely arbitrary. I could have put the origin right here and which have made all my measurements from that position. But because it's arbitrary, but it's important to always know where you're making your measurements from. So you want to define your origin for your coordinate system from the very get-go. So yeah, that's the theory for the reaction forces on a simply supported beam. Not too complicated. So now let me give you some tips to consider when you're in a lab with a setup like this and you're actually trying to make some measurements. First thing I want to talk about is the length of the beam. You know, it might seem pretty obvious if you took a tape measure and you measured the length of the beam. This particular beam measures 93 inches long, and that's definitely true. That beam is 93 inches long. But I don't really care about the part of the beam that is not supporting any load. I'm specifically talking about this part of the beam here that's sticking out past the support. That's not involved in the static analysis. What I care about is the part of the beam that's between the 2 points where the reaction forces are pushing up on the beam or where the beam is pushing down on the blocks. Where are those two forces? Where is the reaction actually being applied? Well, one thing that you might assume is that the reaction force is acting right in the center of the reaction. One thing you might assume is that the reaction force is acting right in the center of the support. So you can take a pencil and put a mark right there at the center of the support. and measure the distance to the center of this support. And the way I've got it set right up here, that was 84 inches, less than the total length of the beam. So probably not a bad assumption to assume that the beam reaction is concentrated in the middle of the pad. It really depends on how much the beam deflects when I stand on it. You can certainly see when I stand on it in the middle goes down. Because of the strength of the material, the ends also flex up a little bit. If it flexes up a lot, then almost the entire beam has lifted off of the support, except for this part right here where it's touching the edge of the support. So if you've got a lot of beam deflection with a setup like this, it might be better to assume that the length of the beam, for any theoretical calculations, is the distance between the supports from the inside of the supports. I really need another person to make sure I've got this in the right place over there. Assuming I've got that in the right place, that's about 80.5 inches for this particular beam. Now, if you're going to be doing an experiment with this setup, you could use either assumption, one that the beam reactions are concentrated at the center of the block, or you can assume that the beam reactions are concentrated at the edge of the block. It's probably somewhere in between, really, because there is deformation of the block underneath the beam, so as we move the load concentrated on the block that's supporting it, it gets pushed down, so some of the beam actually stays in contact with the support, even when it bows up. I'll let the students who are doing a lab decide whether they want to use the center of the support or the edge of the support, but they need to be able to justify that assumption based on some observations of exactly how much deflection is occurring. So that's one thing that you need to keep in mind when you're doing an experiment with a setup like this, is what is the total length of the beam. Another thing that you need to understand is how the tape measure works. And most of us use these things without thinking, but I don't know if you've ever wondered, why is the end loose? I had one student actually say, I don't think the end should be loose, and took a hammer and hammered down these rivets, and that affected the accuracy of the measurements. When you pull or push on the end, it should move a very small distance, and that distance is, or should be, equal to the thickness of the hook on the end. So that when I'm pulling on the hook, I can get an accurate measurement from the position that the hook is connected. When I'm pushing on it, the distance from my finger to the tape measure is the value that's recorded on the scale, plus the thickness of that little part. So it needs to wiggle just a little bit, but not too much, and that amount of distance should be directly related to, is in fact equal to the thickness of that little tab. Another thing that you need to think about is how these scales work. And the value that the bar indicates can seem to change as you move your point of view from the right to the left. So when you're trying to read the scale, it's very important to center your eyes directly over the red line, so you're looking down perpendicular, or at least always to use the same angle of incident viewing, and the easiest angle that I can come up with is straight down. So right now the scale reads 0, but when I put my support on there and the 2x4 itself, then I'm actually weighing the support and part of the 2x4, because only part of it, because the other end is still on that scale down there. And so that we need to subtract that amount of offset from our experimentally measured reactions in order for the static analysis to work, because we're going to neglect the weight of the beam in our calculations today. So one thing I can do is I can just record that value and then subtract it from all my measurements. But the scales have a wheel on them. The wheel can be seen right here, and if I move this to the right or the left, it actually turns the dial. So if I'm moving it here to the left, it increases the reading, and if I move it to the right, it decreases the reading. So what I can do before I start the experiment, if I want to be lazy, and have the scale take care of that offset for me is reach around to the bottom and turn the wheel. I'm turning it right now to make the scale indicate 0 from the very get-go. And so I've actually subtracted out the weight of the beam by tearing or zeroing the scale. So that's one thing to keep in mind. My observation has also been that some of these scales, since they're pretty cheap, don't always give consistent readings, and that's a particular problem when they're on carpet for some reason. I'm not exactly sure why, because the supports are lifted up from there. But so it's always good to go back after you run the experiment and make sure that your initial reading on the scale is still 0, as a way of helping validate the data. So these are some concepts that are related to statics and static equilibrium for a simply supported beam. I hope you've learned something. Thank you for watching.